Today we're going to discuss uh, total hydrostatic force on plane surfaces that is submerged in bodies of water. So considering here we have here your bodies of water, then I submerge an object, then it is submerged. So considering we have a plate arbitrary shape, so we don't know, it depends on the type of object that is being submerged. So completely submerged in a liquid as shown in the figure. So this one is our object, together with its normal view. So we say its normal view, that is on the part of this surface. So I'm going to draw the normal view of this object and projecting that one. Now I draw here the normal view of the object, so that is for this the surface area at this part. So when you look at normal of the surface of this plate, so you will see this irregular shape. So it's an arbitrary shape, so that is, we do not know what type of object and what type of the size of the object that is being submerged in the fluid. Then the plane of this surface intersects to the normal free surface at an angle of theta given shown, and we'll be taking the line of intersection to be the x-axis. Now the absolute pressure above the liquid, we have the given, that is that will be the piece of O. So we have here the piece of O. So this will be the pressure above the liquid, which is equal to your atmospheric pressure, which is, you have your P, atmosphere. And if the liquid is open to the atmosphere, if and only. So since we are trying to consider here if and only, that is open to the atmosphere. Now here we are assuming the problem, the figure is open to the atmosphere. Now the absolute pressure at any point on the plate is given by, we have your absolute pressure, which is your P. So I'm gonna write it here down. So we have your absolute pressure, so that is P, or the pressure, that would be the piece of O, which is your atmospheric pressure, plus your density, gravity, times your height, where our height, where your H, okay, so that the H, this one, so where our H, this one, is the vertical distance of a point from the pre-surface, and we have the Y. Okay, so let's start it here. Let's write it here. This is our H. So this is your H. Then we have your Y. So that is the distance from this point going there to the x-axis. So we're considering this is our x-axis from point O. So we have here your point O here. So this would be the value of your Y. Then assumingly we have here the center of our object. So I'm going to draw here. So this is now our centroid of your object. Then we shall have another point here below, beneath of the centroid. So this will be now our, so this will be our now your center, the center pressure. So at the center pressure, our resultant force, or the resultant hydrostatic force, Fr, is acting. So at this point, we have here our resultant hydrostatic force, which is your Fr acting at this point. Then we have here, since we do not know the area, so we take in the strip here. So this is now our differential area. So we have dA here. And this is now our, well, this the plane surface area. The resultant hydrostatic force acting on the surface is determined by integrating the force. We have force acting in the differential area over the entire surface. So from our pressure equation, so we have your P, which is equal to force over area. So considering here we have the differential area, so we're going to change this one. That will be force times your differential area. So to get the resultant hydrostatic force, we need to integrate this one. So we have here your force now is equal to the P times your differential area. Then integrating this one, so we have your force. Okay, so we're going to integrate the pressure times your differential area, where our pressure is equal to this one. So we're going to substitute that one. So we have now your force is equal to atmospheric pressure plus the density, gravity times the height. Then we have your differential area. Now our height here, taking note, so we can form here a right triangle. So we have here your height, then we have your y, then you have your theta. So to obtain your height, that will be sine of theta, that is equal to your opposite, that will be your h. Then you have your hypotenuse, so that will be your y. So our h is equal now to the sine of theta times the y. So substituting that one to our equation here, so we can rewrite our equation as the integration of the atmospheric pressure plus the density, gravity, so that will be times y sine of theta. So I'm going to change this one to a bracket. So this is becoming your bracket now. Then multiply by the differential area. Then expanding our equations and distributing the integration, so we can that will be, so this will become integration of your atmospheric pressure times your differential area, then plus the integration of density, gravity, then you have your y sine of theta, differential of area. Then we're going to take out what is called the constant here. So bringing out the constant to the integration, so we have your atmospheric pressure times your differential area, then plus the density, gravity, then our sine of theta, then we have your y, differential area. So our force now, or resultant force, we have PO, so differential area, that will be PO, so that will be A, so returning it back to its original state. Then we have here density, then gravity, so this will become your density, gravity, this is sine of theta, times your sine of theta. Since our y differential area, so this is what we call the first moment. So this is the first moment of area, the y dA, which is related to the y coordinate of the centroid, or the center of the surface, by your, we have your yc, which is equal to 1 over your area. You have the integration of your A, then we have your y differential area. Then substituting that one, we have now your YC. So we have here, we're going to attach here the YC, the equation, then multiply by the area. So we can factor this one out. So we have now your force is equal to the atmospheric pressure plus the density, gravity. Then we have the sine of theta. Then we have your YC, or the first moment of area, then multiply by your area. So going back to the figure, determining the YC here in the figure. So that is the distance of our, call this, centroid to the point O. So starting from here, the centroid, so that will be the distance. So this is our YC, the distance from this one. So I'm going to write here the YC, and the corresponding distance of YC to the normal to the surface. So we have here your HC. Now to get the value of your YC, so this is again form a right triangle, and then you have your theta here. So I have here your HC, and we have here your YC. So we're going to do is just do a sine of theta, and we have your opposite, which is HC, and you have your hypotenuse YC. To get the value of HC, so that will be sine of theta. So to get the value of HC, so that will be sine of theta times now your YC. Okay. Now looking back to our equation here, so we have your sine of theta, which is this one, that is sine of theta times the YC. So they have the same of this one, YC. So going to replace that with HC. So rewriting our equation here, so we have now your force is equal to atmospheric pressure plus your density, gravity, sine of theta, then this will become your HC, then times your area. This is now become, writing that one, I forgot class. So this will become HC times the area. Now our HC, so looking back to the figure, so it became the vertical distance of the centroid from the pre-surface. Okay, so this is your centroid reflecting with this one. So we have your vertical distance, and therefore we can conclude that the magnitude of the resultant force acting on a plane of a surface completely submerged in a plate in a homogeneously constant density of the fluid is equal to the product of the pressure at the centroid of the surface and the area of the surface as shown in the figure. Now, the pressure or the atmospheric pressure, in some calculation, which can be ignored in the calculation since it acts on both sides of the plate. So, for example, if I have, I'm going to draw a sample here that we're going to ignore the use of the use of the atmospheric pressure. For example, I have here a dam, let's say, okay, then I have here a gate. So this is all exposed to the atmospheric pressure. Okay. So I have your bottom of your seabed, or let's say the bottom of the seawater. Then we have here. Now the force acting at this point. So we're going to cancel out the piece of O, since this side is exposed to atmosphere, and this one is also being counteract by the atmospheric pressure. So you have here your wall, let's say this is your dam, and it is being blocked by a gate here. So piece of wall will be cancelled out. So we're just in if the problem is stated that we have the surface of water here, which is your gate, is submerged, or let's say it is a surface that is submerged in here at the bottom. Okay. So at this type, so if you want to get the pressure, or we can say the total pressure or the total resistance of the pressure on the surface, so that will be additional of the atmospheric pressure. So it depends on the problems, but this one, okay, so take note of that one. Next, we need to determine the line of action of the resultant force Fr, or Fr here. So we need to determine the line of action of this one. So when two parallel forces system are equivalent, so if they have the same magnitude and the same moment about any point, the line of action of the resultant hydrostatic force in general does not pass the centroid of the surface. So it lies underneath the pressure, where the pressure is higher. The point of intersection of the line of the action of the resultant force and the surface is what we call the central pressure. So we have here the central pressure. So the resultant force Fr, so that is acting below the centroid, where your pressure acting here. So we have here your Fr beneath the centroid. Now the vertical location of the line of action is being determined by equating the moment of the resultant force to the moment of the distributed pressure force about the x-axis. So we have here the moment, so we have here Fr. So I'm going to draw a line here again, from here going there. So the distance from Fr to this projected line from O, we have your Yp. The vertical location of the line of action is determined by equating the moment of the resultant force to the moment of the distributed pressure about the x-axis. So from here we have equating, we have your moment from your horizontal force for the resultant force here. So we have the corresponding distance, which is your Yp. So taking a moment, starting from here, going here, we have your moment. Now, it is also stated that if these forces lying in the same direction, so if they are parallel, so they can be an equal amount, so or equal values. Then for the another, we have the differential area of your pressure. Since our pressure here, now I'm drawing here a line, so this is the pressure usually. So we have a varying pressure acting on the surface of the plate. So I have here the varying pressure, so that is the pressure acting on the surface of our plate. So we have your differential area also, that is acting on the differential area also. So from there, so taking the moment, okay, so we have your moment from O. So going back to the figure, so we have your moment from O here. So that will be the distance of Yp. So you have your distance of Yp. So rewriting that one, so we have your Yp. So that will be multiplied by the resultant force. So this is equal to the value of your Y. So we have the distance, and this pressure, okay, our pressure is acting on this area. So we have here the pressure here acting in this area, so they are in parallel action, so another from your pressure. So that will be the pressure times your differential area times the value of your y. Since this is our differential area, we have your corresponding differential pressure at this point. So this is now your force acting the differential pressure at this point. So I'm going to draw here. We have your differential pressure or dP, or let's say not actually the differential, just only a pressure here acting. Sorry about that one. So we have here acting the pressure which is equal to the value of this one. Okay. So our pressure here is equal to the atmospheric pressure plus density times the gravity. So I'm going to label this one. So the pressure here is the atmospheric pressure plus your density, gravity times your height. So that is acting on this point at your differential area. So going back, equating that one, so we have your integral. Okay. So since it's a differential, so we have your integral. Then we have the distance that is y. So here we have your y times the pressure. So since we need to find the force, since it is equal, so we have your y times the pressure times the differential area. So the units of this one, this is pressure, this is already Newton per square meter, then will be multiplied by square meter. Okay, so it will be cancelled out, then multiplying by the value of y, which is also meter. So we have the unit now in Newton meter, so that will be y times the pressure, and you have your differential area. So expressing our equation to the value of your pressure, so we can rewrite this one as your y times the value we have your atmospheric pressure plus we have your density, then the gravity, and also since it is the height, the value of your height, that will be y sine of theta. Then we have your differential area. So y sine of theta, that is also equal to your height. So going back to the figure, we have this one. Okay. Okay, so let's rewrite our equation. Okay. So then distribute the values here. So we have here your y is above. So we have the differential area here, and then plus the integral of your density, gravity, then distribute. We have your y squared here, then multiply by sine of theta, then differential area. So let's rewrite it equation. So bringing out the constant here from our equation. So we have your y, the integral of your so this will be feasible, or the atmospheric pressure times your y times your differential area plus your constant here. We have your density, then the gravity, then that will be the sine of theta. This is also constant. Then we have your integration of your y squared, then the differential area. Then we have now our yp times the resultant force. Now is equal to P sub O. Since this one is already equal to the, going back there, we have your yc, that is y differential area, so this will become your yc. Okay. Then multiply by differential, then we have here plus the density, the gravity, then you have your sine of theta. So this one, the y squared dA, so this becomes the second moment of inertia, second moment of area, or also called the area moment of inertia. So this will become now your I. So it will be Ixx. We have here your O. So your this one, that will be your I 0, that will be equal to the integration of your y squared, then you have your differential area. The second moment of area, or the moment of inertia about the x-axis, are widely available for common shapes. So you can look that one in any engineering handbooks, but they are usually given about the axis passing to the centroid of the area. Fortunately, the second moment of area about two parallel axes are related to each other by a parallel axis theorem. So when which this case, so it can be expressed as this equation. We have your this one, so that will be equal to your plus your y squared here, c times your f, okay, where this one, so this is the second moment of area, right, where this one is the second moment of area about the x-axis passing through the centroid of the area. Then we have your yc, or the y-coordinate of the centroid, is the distance between two parallel axes. So looking back here, our figure here, you have your yc here. Okay, so you have your distance from here going there. I forgot to put here. We still have here our area. So we have here your A. Okay. Now looking down, so I'm gonna name this equation as, so let's say this is your, I'm gonna change also the FR here. I'm changing that one here. Okay, so that is the force resultant from here. So this one your FR. Okay. So I'm gonna name this equation. I'm gonna name this equation as your EQ1, and this is, call this equation 2. And this is our equation 3. So I'm going to highlight this one so that it can be equally aware. Now, substituting this equation to equation 2, so I'm gonna write here equation 2, substituting. Substituting the equation 1. So we have here the equation 1, 2, and equation 3, this one, to the equation 2, this one. So substituting that so that we can get the value of your yp. So expanding our equation, so we have now your yp, so that will be your yp, then it is multiplied by the value of your fr, which is your atmospheric pressure plus your density, then we have your gravity, then you have your yc, then sine of theta, then it is multiplied by a, which is equal now to atmospheric pressure of your yc, that will be times your a, plus your density, then you have your gravity, sine of theta, then the value of I, xx. So that will be, the I, x, x of bc plus our yc squared times your area. So let's transpose the value of this whole equation to the other side. So we have now your yp is equal to the atmospheric of your yc area plus your density, then gravity, then we have your sine of theta times the I x c, then plus your y squared c, and it is divided by the atmospheric pressure plus the density, gravity, then you have your yc, sine of theta, then we have times a for the area. Then expanding this part of our equation, so we have your yp that will be atmospheric, then you have your yc, the area, plus we have your density, gravity, times sine of theta, then times your ixc, then plus density, gravity, so we have here your yc squared, then that will be also sine of theta, so yc squared, then that will multiply by also your area here, and it is divided by, so that is divided by the same equation here. You have P sub atmospheric plus density yc, then you have your sine of theta times your area, and we can factor what is our common in our equation here. So we have your yp, so we have your yp, so we can factor, or let's combine this one. So we have here, we have your P sub O yc, that will be plus your density, gravity, c squared, then you have your sine of theta times your area, plus density, gravity, then we have your sine of theta of xxc, then it is divided by this equation. Okay. And we can factor out what is common here at this equation. So from here we can know what is our common. We can factor it out. So we have here your area, so that will be also the common here, and also your yc. Okay, so let's do factor that one. So we have your yc, then you have your area, then we multiply by the atmospheric pressure plus your density, gravity, then yc sine of theta, then plus we have your density, sine of theta, then your I xc, and it is divided by, again, the same equation we have here. Now let's try to separate it from the distributed to the denominator here. So we have your yca area times your atmospheric plus your density, gravity, then you have your yc sine of theta, then the denominator for this one. So, okay, so you can separate it like this. So since they have only the same denominator, then you have the plus density, gravity, then you have your sine of theta I xxc, then divided by the same also here. Okay. So we can cancel out what is common. So we have here your common here. So they are 0 now. Cancel that 1. And what is left is RYC. So we can write our equation as we have your YP now, which is equal to your YC. That will be plus our value for this one, that will be density gravity. We have sine theta. So we can also express this one as I c over x, then divided by that 1. So we can bring this one under to be as a denominator of this equation, so they are the same. So I can write it like this. We have your density here, gravity, you have your sine of theta. Okay. So they are the same. It is a reciprocal value from this one going down here. Then we can rewrite it as your YP now is equal to your YC, okay, plus your IXXC is divided by, so we can distribute this denominator to each of these values of equations. So we have your density, gravity, you have your sine of theta, then plus you have your density, gravity, YC, sine of theta would be equal divided by your density, gravity, sine of theta, and this is multiplied by your area. So let's do cancel what is common here. So we have density, this one, also this one, and this one. So we can write now our equation, your YP is equal to your YC, then plus IXC, then it is divided by this will be YC, which is left, and this will plus atmospheric pressure divided by your density, gravity, and we have your sine of theta, and this is multiplied by your area. So let's box this equation. We have now the value, to get the value of your YP. Now for the piso of the atmospheric, which is equal to 0, which is usually the case when the atmospheric pressure is ignored, the equation simplifies. So in the case that our atmospheric pressure, so if I'm going to write it here, or if our atmospheric pressure is equal to 0, so our equation is simplified into, you have your YP, it will be your YC, IXXC. So this will be now your YC times your area. So you can simplify another if and only our atmospheric pressure is stated as 0. Knowingly that our YP, this one, is the vertical distance, so going back to the figure, so we knowing the vertical distance of the center pressure, we have here the vertical distance, that is your YP. So it can be determined by using your trigonometry. So we can use our HP. So if we're going to draw a triangle here, see, we have your theta here, then I have your value of your, so we have your value of here, your HP here, and I have here your YP, okay. So we can determine it by using the sine of theta that will be equal to your opposite. So, and we have your yp under, okay, to get the value of your HP. So our HP will become your is equal to sine of theta times your yp to get the value of your HP. So this is the, call it, the vertical distance. Okay. Sorry, this is the vertical distance from the center pressure acting here going to the top of the surface of the water. So this will be the location of the center pressure. So this will be now our HP. So our HP will be the location of your center pressure. So if we found out the value of your YP, so we can be able to determine the location of your HP, which this is the parallel call this normal to the surface of the liquid. Now for the values of our ice, this one, okay, for the value of this one, so we have here, I will be bringing down the table here, so you can refer, so of different size and shape. So we have here the values of your IX. So we have here the values for your, for example, we have here your rectangle surface, okay, and we have your circle. So we have your value on this IXC. So we'll be using this one. So this is already constant values that will be used, where the value of your A is the sides of the value here given, and the given length of your rectangle, and we have your B, your width here, that is raised to cube. And also for if we have, you will be using a circle, so the same also will be using here. So we have here the values, so that will be pi r to the fourth divided by 4. And if the plate is an ellipse, so it's the same also, we can get here, so it's already given here. So you just only have to do is plug and play to our equation given here to get the value of your YP. And also we have your given area here, so for each shape, so we have also given here the area of the mostly common shapes that will be used in our problem solving. By looking at the overview of our discussion, so try to refresh. Okay, so we started here, going down there. Okay, so I made the derivations here, so in clearly for you, in order for you to follow. Okay, so we have here the summary.